In today's lesson, we'll continue what we started in the last lesson, heat energy calculations. Today we'll be moving into calorimetry calculations, and part of today's lesson includes giving you some background information, some help to get started with your ice cream Prelab calculations. Make sure, if you're grading somebody's paper, that you put your name in the lower right-hand corner, last name first, and you circle it. Okay? All right. Let's analyze the problem here, okay? So we first have a 4.75 gram sample of water. So that is mass is equal to 4.75 grams. And it starts out at 45 degrees C. So temperature initial is 45.0 degrees C and is heated to boiling. Well, that means the final temperature is the boiling temperature. So temperature final is 100.0 degrees C. And then it is boiled completely into steam. So that's a whole different set of equations. But if it's boiled into steam, that just means we have a different equation. So one of the equations we're going to need is for this temperature range here. Okay, so temperature, change in temperature is going to be final temperature, temperature final, minus temperature initial. And yes, we'll fix that noise right now. Okay, all right. So to find the change in temperature, then we want to take our final temperature, which is this. We want to subtract the initial temperature. And we see we have 55.0 degrees C. Now this is why it's important to write it down on paper when you do the math. I mean, it might seem like really simple. I can do this in my head. But if you don't do it on paper, or if you do it just in your calculator, not see it on paper, you might not realize that's a significant zero. Okay? Always show it on paper. So for me, you have to show it on paper. Okay? So I can see you know how to figure out what the significant digits are. All right? So we now know our change in temperature is 55.0 degrees C, and it's a positive number. If we were going down in temperature, it would be a negative number. Okay? So now we're going to need for the change in temperature from this range here, so for heating water, we need the equation Q equals mass times specific heat times the change in temperature. For boiling all the water, we need the equation Q equals mass times the, in this case, enthalpy of vaporization. Okay? All right. And then the total energy to be put into the sample of water is Q for heating plus Q for boiling, or the phase change, and that equals Q total. Okay? And that's what I told you yesterday. You had to add them together. All right? So that's kind of a new equation here. Okay? You need to know that the total Q is the sum of all the other Q's. So if so let's say, for example, we were taking, that's not what we're doing here, but if we were taking a sample of ice at negative 10 degrees C, and I want to heat it up to steam at 110 degrees C, I'd have 5 Q's that I'd have to add together. I'd have the Q for heating up the ice to the melting temperature. I'd have the Q for changing the ice into water, phase transition. I'd have the change in temperature Q that goes from 0 degrees, the melting temperature, up to the boiling temperature of 100 degrees. I'd have the Q for the phase change from liquid water to gaseous water for boiling. And I have the Q for raising that water that's now steam another 10 degrees to 110 degrees C. And you'd add all 5 of those together. That makes sense? All those have different specific heats for the temperature changes and different enthalpies for the phase changes. Okay, so right now we just got one phase change and one heating up thing, okay, up here, range. So let's start with this equation here. So we're going to say Q equals mass, which is 4.75 grams. And guys, graphite is cheap, okay? Graphite is cheap. Don't try to spare the graphite, okay? Use it, all right? That's your pencil lead, right, okay? Write stuff down. Write it out like I wrote it out. Don't just say, oh, Miss Ted wrote it out, I don't need to. You have to write it out, because when you get to these complex problems, if you don't write out a step-by-step plan, you're not going to be able to figure it out. If you look at a problem and it looks complex, and you say to yourself, I can't do that, start writing out stuff. A lot of times the light just comes on when you write out a step-by-step process, okay? Figure out where you're going and all those steps to get there. That's it. So the math for the math for what we're doing here in chemistry is not hard. It's just a lot of different things you're putting together to make up the math. It might look like it's hard, but we're not doing calculus here. Okay? We're doing basic algebra. All right? Not even algebra 2 stuff. Just basic algebra 1 stuff, okay? Now we will do some algebra 2 stuff kind of later in the semester, but for most of the year, most of the semester, we're just doing algebra 1 stuff here, okay, at best. Or just, in this case, pretty much, multiplication and division, but it's just algebra setups, all right? So anyway, there's our mass, and then times the specific heat. Well, the specific heat for liquid water, so this is the liquid phase here. The specific heat for liquid water is 4.18 joules per gram per degree C. And then we need the change in temperature we figured out was 55 degrees C. And we're going to put these two here over 1 so that it's easier to see how we're going to cancel out. I'm going to cancel out grams here and degrees C here. That's the algebra part. The algebra part is the dimensional analysis part. We call it dimensional analysis because we can cancel out units the way you also canceled out x's and y's when you were doing it, basic algebra. Okay? That's now we want to do the math. And this math, all the numbers are on the top of the fractions, so all we're going to do here is multiply. Okay? Everything's going to be multiplied. All right, so we've got 4.75 times 4.18 times 55.0, and we get this fairly large number here, or what seems to students like a large number. It's not really. Large is relative, okay? If this were that many pennies, that's only $10 or $11 close to it. That's not a lot of money, right? So large is relative. All right, so we've got all the units are canceled except for joules, but this number is a measured number. It has 3 significant digits. This is a calculated number with 3 significant digits. This is a calculated number with 3 significant digits. We need our final answer to have 3 significant digits. So we're going to underline everything past the first 3 digits, and we're going to round it off to 1.09 times 10. We're moving the decimal place. Because we're getting rid of a digit in the ones place, we've got to move our decimal to just to the right of the non-zero digit because we're writing our answer. It's required that you write your answer in scientific notation. 1, 2, 3. We're moving it right there right to the right of the first non-zero digit. So it's times 10 to the third power. Okay? So that's our Q1 here, our Q heating here, okay, that we've done this one. All right? Now we've got to do this Q for boiling. And so our mass is the same, 4.75. We didn't take away any of the water. Is there a question?
No, she said she got the first one right.
Okay, good. And now we need the enthalpy of vaporization here. Let's see, I think I gave you all that yesterday.
Yeah, you did.
Find where I gave it to you. Was it 2.05 joules? No, that's a different one.
It's like 20 something.
Yeah, 2260, yeah. Right? Mm-hmm. Okay, here it is. 2260 joules per gram. Okay? And so we just cancel these units. This is even simpler because I don't have a third step there or a third unit of measurement. Okay, we're going to do that math. So we've got 4.75 times 2260, and we get 10735. And there's, wait, was that right? No decimal place at all? Yeah, no decimal place, okay. All right, and so that's joules. We need 3 significant digits. This number only has 3. And because this is a 0 in the ones place with no decimal place, you have to assume that has 3 significant digits as well. Okay, we assume there's no 4th significant digit here. Okay, so we want to get rid of everything except the first 3 digits, 1, 2, 3, underline, draw an arrow, move our decimal so that it's just to the right of the first non-zero digit, 1, 2, 3, 4 places. So it's 1.07 times 10 to the 4th joules. Okay? Got that?
Yeah.
All right. Now we need to add everything. So we've got this. Now we need to add these things together. Now you can do this with your calculator, but you need to keep it with significant digits too. All right? And I haven't shown you this, but it shouldn't be that hard. I've shown you how to keep up with digits when you don't have zeros, right? I mean, you could put zeros in there, I suppose, but really you need to, you can use arrows instead to keep up with them to make sure everything works out. So, to keep up with significant digits, I'll go back kind of this number where I'm going to get rid of this 2, but that 2 is going to become an arrow for me. That's how I'm going to do it. Okay, 1, 0, 9, and I'm going to put an arrow right here in place of a 0 so that I'm not misleading anybody about the significant digits that are there. Okay? Because if I put a 0 there, that would not be significant. Okay? It would be lying about precision if I left it there. Although a 0 in the ones place with no decimal wouldn't really matter because you'd assume it's not significant anyway. You should. So it's really okay in this case to use a 0 because in the end you're going to know it's not significant anyway. All right? And so for this one then, this is going to have 2 arrows, 107, and 2 arrows. All right? That makes sense? And so we get 1179. And these are joules here, joules and joules and joules, okay? But now there are 2 insignificant digits. Did I do that right? No, 1. Huh? Oh, I forgot the arrow there, didn't I? Okay, that's what I'm missing. Okay? So, but I've got 2 insignificant digits here, okay, because I've got an empty slot right here. So those 2 are going away. So I've got to write my answer again in scientific notation. I've got to move the decimal place 1, 2, 3, 4 places. Draw an arrow. And we get 1.18 times 10 to the 1, 2, 3, 4, 4th power joules. Okay? And that's our final answer for the amount of energy that's going to be used or given to the water to make this change in temperature and then getting it all the way up to steam. Okay. All right. So why didn't we line up? You're asking me why didn't I line up these 2 decimals? Because the order of magnitude here is different. You can't just line up the decimal places because it's the 3rd and the 4th. Okay. So if you put this number in your calculator and put this number in the calculator, you would get something pretty close to this number. The only reason I did it this way is so you could see how many significant digits you're supposed to have once you add them together. Okay? If you choose to put zeros here, you still have to keep up with how many significant digits you're going to have at the end. That makes sense? So I probably wouldn't count it off if you put zeros here for the purpose of addition. You got to be careful about those significant digits, though. Okay? Any questions about that? This is the way that I've kind of shown you to handle zeros you shouldn't have. And that's why I put them there, like that. You don't have to do it that way. I kind of recommend it. It'll keep you from being in trouble with significant zeros and significant digits. All right? So you added up 1.09 and 1.07, and you got 216 something, right? Okay. So you just did the math wrong. Okay. So you can check it with your calculator, and if you don't have a reasonable answer, you start scratching your head and say, what's going on? And then you can stop in here before school or something and ask me, what's going on? And I could help you with it, so you get you straightened out. All right? So that's really, I mean, that really, you were probably taught that in elementary school and just forgot. Okay? If you don't use it a lot, sometimes you do forget. So our total is 1.18 times 10 to the 4th joules. All right? So let's figure out how many points this thing is worth. Now, guys, listen carefully. I'm not going to count off if you didn't do this time. Okay? Warning. In the future, I will. Okay? Starting now, when you have a list of knowns and unknowns, like this, I want you to write them out. I want you to make a list of knowns and unknowns for the future, okay? It's going to help you. When we get to gas laws, you're going to have to do that too. We'll get back doing this kind of thing. So if you have a list of knowns and unknowns, write them out. It'll help you organize your problem, all right? So that's what I expect to see. I expect to see a list of knowns, and I didn't write out the unknown, but I kind of wrote it out here because we're trying to find this Q, all right? I want you to always, it's required that you write out the equation in the with the variable form or the dimensions form, okay? Where mass is written here. So Q equals mass times specific heat times change in temperature. I expect you to see that equation written out without any numbers plugged into it, okay? And then you plug the numbers into it. You with me? That's what I want to see. I want to see this equation if you have to add up different Q's. I want to see all the equations you're going to use to set up the problem. All right? It will help you to organize your mind to find the answer. So it's not just me giving you points for doing it. It's helping you to do it better, so when you get to the test and you need it later in life, you kind of got a method for doing it, right? So these are tools. These are tools for problem solutions, okay? Use them. Don't spare the graphite. Here's a question for you. What do you use to hammer a nail? A hammer? Why not your head? It would hurt? You might die? Okay. It's not the right tool for the job, is it? You want to solve problems? Doing all these steps I'm showing you is the right tool for the job. You got it? So unless you want a bloody forehead, you know, use the right tool for the job. All right? I'm giving it to you. It's free, right? You got a toolbox now with tools. Use them. All right. So let's figure out how many points we're going to give everything here, all right, for today. For the future, I need to see the addition written out, okay? I need to see the equations written out. But for right now, we're going to count just the math itself. So we've got 4.75 grams and canceling grams. That's 1, 2, 3 points. It's over 1. That's 4. There's a times operator here. That could be a dot. That's 5. 6, 7, 8, 9. Well, you could put this in here without a dot, so I won't give that one. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 for the underlining, 20, 21, 22, 23 just for that part. Okay? Then here's the part where we figured out the energy required to boil the water away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is the underlining, 13 for the units of measurement, 14, 15, 16. Okay, so that part's 16. All right? Doing the math for the final part, since I didn't, you could do it in different ways. You really should be adding them in some fashion and showing me the addition vertically. I'm not going to count it this time. I should, because you've been taught that before. Okay? But I won't do it today. We're just going to count the final answer here, number and units of measurement. Okay? But remember, in the future now, I expect to see all the math. Okay? Not just part of the math. Got it? It might seem simple, but if you've got to add 2 and 2, put it down on paper. 2 and 2 plus 4. 2 and 2, 2 plus 2 equals 4. Put it down on paper for me, okay? Show it to me, because I'm from Missouri. All right? All right, so 23, 16, and 2. That comes out to be a total of, what was it, 41? Any questions about this solution? Yes.
I still don't understand the way you added it. I understand because it's 10 to the fourth and 10 to the third, but I don't understand like why.
Why the arrows?
Not the arrows, like the way you position the numbers to add it.
Okay. I'll tell you what, take a calculator out. If you don't understand why there's an extra slot right here, okay, put this number in your calculator just like that. Put in 1.09, and if you know how to use that exponent key, you can just put in E3 if you want to, and hit enter and see what you get. Okay? Let's see if my calculator emulator will do that. So I'm going to put in 1.09, and let's see here. This is, on this calculator, that's the exponent button. So when I put an E like that, it means times 10 to some power. So 10 to the third, and I get that number. Okay? And so we'll put in that other number as well, 1.07, and then that double E button gives me that exponent key. And we'll put in 4, and we get that number. And so you see how those two numbers line up if you were to add them together? Aha. So that's why they line up like this. Does that make sense? Okay. Any other questions? That's a good question, by the way. If you don't understand something, if you don't ask, well then, you're just setting up yourself a failure. You need to ask if you don't understand, okay? Good. Now, when we're talking about the way that heat energy behaves, we have to think in terms of theory, okay? It's things that aren't so much real, or things you can't put your hands on. They're real, but you can't put your hands on it, okay? You can't touch it, all right? You can't handle it. You can't see it. You can't taste it. Energy cannot be measured directly, all right? But we know by the way that we work with it that it behaves in a certain way. And so the underlying way of thinking about things, so this is a model. The way we think about how this happens works something like this. That when we're looking at heat, we look at one thing at a time. All right? We look at the heat either going into something or out of something. All right? And so the thing that's going into, we call the system. Every place the heat is going into or out of that we're looking at one time is called the system. So we have something called the system. Okay? And that's the place that we're going to examine. That's our system. All right? For the purposes of theory, thermochemistry or thermodynamic theory, if it's not in the system, it's in the surroundings. All right? For the purposes of thermodynamic or thermochemical theory, if it's not in the system, it's in the surroundings. Okay? If I'm boiling a pot of water on the stove, the water in the pot, it doesn't include the pot, just the water in the pot is the system. All right? Everything else, the pot, the stove, the air around it, the kitchen, the house, the neighborhood, the city, the country, the planet, the universe, it's all the surroundings. All right? Make sense? Everything. All right? So taken together, all of this, system and surroundings together, make up the universe. And one of the thermodynamic laws of the universe is that energy, or really mass energy, is never lost. You can move energy from one place to another, as in moving from surroundings to system or system to surroundings. You can even change mass into energy, but you can't get rid of it. There's a finite amount of mass energy in the universe. Okay? Got that? So if we want to look at what's happening in a limited surroundings, we have to insulate it. Okay? And so we kind of create a mini universe to do that. And a little mini universe we call a calorimeter. Okay? And the reason we call it a calorimeter is because instead of measuring heat in joules, it used to be measured in calories. Okay? Calorimeter. Now, a really simple calorimeter is a styrofoam cup. And a lot of times in chemistry labs, You'll do calorimetry using a plastic cup. I mean a styrofoam cup. And so let's say, for example, we wanted to find out the heat capacity. Remember, that's our CP in our equation, right?
Yeah. Pretty good little cylinder right
All right. We wanted to find a heat capacity of, I don't know, let's just say copper. All right. So we find a chunk of copper. So here's my chunk of copper. All right. And I want to take that chunk of copper and I want to put it in some water. Okay. And this is our little calorimeter. Now, before the copper goes into the water, it needs to have a different temperature than the water. Okay? So let's say our beginning temperature for the water, so temperature initial for the water in the calorimeter is, all right, all right, we're going to start with water initial at 25 degrees, okay? The mass of the water we're going to have is 100 grams. Okay, and our copper here, initial temperature of copper is, let's say, 100 degrees C. See if I've got that right in my example here. Yeah, 100 degrees C is where we're going to start. All right. And the mass of the copper is 15 grams. All right. And I did 2 digits past the decimal here. Let's move up here and make that 2 digits past the decimal on our water mass, okay? All right. Now, in a practical sense, you know what's going to happen when you take a hot piece of copper and put it in cooler water, right? What's going to happen? Okay. Well, it won't steam up because the copper's only at 100 degrees C. So we're not going to boil the water. If it were above 100 degrees C, it would boil the water, right? But what will happen to the temperature of the copper?
It'll cool down.
It'll cool down. What will happen to the temperature of the water?
It'll get hot.
It'll get warmer. Okay? So the water's going to heat up, the copper's going to cool down. And when will all that stop? All that heating up and cooling down?
Never.
When they are they will eventually reach, I guess technically maybe never, but in practical terms, they do reach what's called an equilibrium. Okay? They reach what's called an equilibrium. Now you need to know that term equilibrium because that's really important in what we do in the sciences. Equilibrium. Okay? It's a kind of balance. All right? And so there's a point where the temperature is going to reach equilibrium. At that point, the temperature of the copper and the water will be the same temperature. Okay? And so the final temperature is going to be 26.02 degrees C. So this is our, let's call it temperature EQ for equilibrium temperature. That is going to be the final temperature for the water and the final temperature for the copper. Okay, because they're going to be the same temperature. So our equilibrium temperature, what did I say, was 26.02, right? Okay. Now, we already know the heat capacity for water when it's in liquid form. We're going between 100 and, well, we can't get over 100, obviously. 25 degrees is where we're starting. Actually, we're going to end at 26.02. And so in that range of temperatures, the specific heat of water is what? 4 point something. What is it? 1.8. You need to memorize that, okay? 4.18 joules per gram per degree C. Okay? That's the equilibrium temperature. After I put the copper in the water, eventually the copper cools down, the water heats up until they reach the same temperature. That's the equilibrium temperature. So that is the final temperature for the water, and it's the final temperature for the copper, because they're both going to reach the same temperature. Does that make sense? Now, we have everything we need to find the specific heat for the copper. Okay? So let me show you how that works. Since what we have is two different systems interacting together, right? And you could think of this as this is the system and the water is the surroundings, because we've got an isolated system. We've insulated everything. Okay? And so if we have Q equals mass times specific heat times change in temperature, okay? The Q that is gained by the water, is going to be the same amount of energy that's lost by the copper. Does that make sense? The Q gained by the water is the same amount of energy that's lost by the copper. Does that make sense? Because the water's heating up, the copper's cooling down, right? So we're going to say a negative Q for the copper. All right? That makes sense to you? The energy is not going to go any place but right here in our little mini universe, because the amount of energy in the universe has to stay constant. You got it? All right? That being the case, then we have everything we need to calculate the specific heat of the copper by setting this equation for water equal to this same equation for copper. All right, so let's do that. Here's the mass of the water. I'm going to put MH2O times specific heat H2O times the change in temperature for H2O. Okay, and that's going to equal the negative of the mass for the copper, which is Cu, times the specific heat for the copper, times the change in temperature for the copper. All right? Does that make sense to you? All we did was take this equation, because the energy gained by the water is the energy lost is equal to the energy that's lost by the copper, and just plugged in these values here. Got it? Huh? Oh, I'm sorry, yeah. Okay. Let's look at what the change in temperature is for the water. Okay? Change in temperature for the water. All right? So for the change in temperature of water, we're going to start at 25 degrees C. That's our initial temperature. And we're going to subtract that from the final temperature. Remember, final minus initial, right? That's always temperature final minus temperature initial. So the final temperature for the water is 26.02. Yeah, 26.02 degrees C. And we're going to subtract the 25.00 degrees C. And so the change in temperature for the water is 1.02 degrees C. Does that make sense? Hmm? All right. Okay. Now for the change in temperature of the copper, that's still temperature final minus temperature initial. Temperature final for the copper is also 26.02. But the initial temperature for the copper is 100 degrees. Okay? So what's the change in temperature for the copper? Negative what? Everybody has calculators? The more you get a chance to practice with the calculator, the more you should. Every time you practice, you're preparing for a test. What? It's a 73 and something. What is it? 73.98. Need to put it in your calculator and be sure. Okay? So that's our change in temperature for the copper. We can plug everything we need in here except for this CP right here and find the CP for the copper. Okay? So now, this is just algebra. Okay? You've learned algebra. Okay? It's a prerequisite for this class. Plug all the numbers you have now into this equation and see if you can find the CP for the copper. Okay? Find the specific heat of the copper based on these numbers. All right. This is plug and chug. All right, and then basic algebra. Okay. Shh. I'm gonna send you guys back to your algebra teachers now. Y'all can do this stuff. All right. 100.0 grams. All right. The specific heat for water is 4.18 joules per gram per degree C. Okay. The change in temperature for the water we determined was 1.02 degrees C. All right. Now to make it easier, we always put these kind of things over 1, right? And that allows us to cancel out grams and degrees C over here on this side. Got that? All right. Now, over here on this side, a negative times each of these terms will make each of these terms negative, right? It's like multiplying each of these terms by -1. And so the mass of copper is going to be a negative number. So the mass of copper is 15 grams. We're going to say that's negative 15.00 grams. The specific heat for the copper is what we're trying to find. CP for copper is what we're trying to find. And the change in temperature for the copper we determined was negative 73.98 degrees C.
But the negatives cancel out, right?
They will eventually. All right. Now, this is also a negative right now. Got that?
Yeah.
Everything's negative over on this side. Okay. Now let's collect some terms. Okay? We're going to collect these terms by doing the multiplication here and collect these two outside terms by doing the multiplication there. Got that? All right. So we're going to multiply all these. Let me clear out the calculator here to kind of see the screen a little bit easier. All right, so 100 times 4.18 times 1.02, and that'll give me 426.36. And over on the other side, it's a negative 15 times a negative 73.98. So, can't do it that way. Hold it. Keyboard problem here. There's our change of sign. Okay, while I'm here, let's be clear on something. There's a button on your calculator that means change of sign, and that's different from the button on your calculator that's for a negative number. Okay? If you're going to change the sign of a number, you need to use this button on this kind of calculator. Your change of sign button may be plus, slash, minus. There's different buttons on there to mean change of sign, but you can't use them interchangeably on most calculators. Okay? So that's a change in sign. That's a negative 15.00 times and a change of sign for 73.98. And we get a positive then, 1109.7. Let's go back to the paper and look at it. What? All right, bear with me now. Bear with me here. All right, so we got this number. Now over here, the only units we have left are joules. And over here, we can't get rid of these two measurement units, so we need to keep grams times degrees C, and then times the negative of the CP for the copper. Okay, that's a capital C, little u. All right, now, what we want to do is to get the CP by itself. And the way that you isolate the unknown, remember that term?
Yeah.
Isolate the unknown. When you're solving for an unknown, you want to isolate the unknown, which means you want to get it on one side of an equal sign all by itself. So if I want to get this unknown all by itself over here, I need to divide both sides of the equation by this number. Okay? So I want to take this side of the equation here. I'm going to divide it by 1109.7 grams. And I'm also going to divide it by the grams, also by the degree C. Okay? And I'm going to divide this side by the same thing, 1109.7 grams times degree C. Okay? Now, since this number and this number are the same, so on the top and bottom of a fraction, that number cancels out. The units of measurement of grams cancel out and degree C cancel out, leaving me with the specific heat by itself. You got that?
Yeah.
All right. To get the answer over here, I just need to divide this by this. So, 426.36 divided by 1109.7. Okay? All right, so that's the answer I get. But I need to keep the units. Okay? Joules per gram per degree C. And if you look at the units of measurement in the water's CP, they match the right units of measurement. Joules per gram per degree C. That's what a CP should be in. Okay? Now, I still have to round it off. I go back to the original problem and look for the measured or calculated numbers with the least digits. These two have the least digits. There's only 3. All right, everything we did was multiplication and division. So we're going to round this off to 3 digits. And so our final answer is 0.384 joules per gram per degree C. And that equals the negative CP for copper. Now there's a problem with a negative, and so we have to ask ourselves, what's reasonable? Here's the reasonableness test. The copper up here was losing heat energy, right? And so it shows it being a negative. But CPs are not negative, okay? It's negative only because that side of the equation was negative. So when you do the reasonableness test, you say, wait a minute, that's because it's only showing up as negative because it was losing that energy, okay? So it's actually just CP is equal to that number. It's not a negative number. It is a positive number. But what you're doing is you're saying that side of the equation was negative so that this would turn out this way. Okay? Just being reasonable. Okay?
My calculator got a longer number than what you had got.
That's okay. The question is, why did my calculator have way more digits than mine did? It's okay. You may have 6 more digits than me. It's still going to round off to that same number, right? Yeah, I've got my calculator on the computer, my emulator on the computer here set up to give me fewer digits just to be easier to see and read, okay? Some calculators are going to have fewer digits, some more. You do not want to have your calculator set up to automatically round. You want to have all the digits on there it'll show, whatever that happens to be, okay? All right, any questions? All right, you want to check and make sure we're right? You want to look up, anybody want to look up the specific heat for copper?
I will. I got you.
Just type in specific heat copper and see what pops up. So if you look it up, in some places you'll get 0.385, in some places 0.384.
What is that?
That's the actual specific heat for copper. Okay? Pretty good. And we just have some rounding errors. It's called the propagation of error. We talked about that. We're going to get slightly off from what the actual value is probably. But not by very much. We did a pretty good job here with our little experiment, didn't we? All right. So having done that, then let's talk about your ice cream lab. You have to be able to solve your pre-lab problem. And everybody has a unique pre-lab problem. Okay? You solve it the same way. But because you're starting with different numbers, everybody may have a different answer. Okay? So, here's the difference in what we've been doing in the ice cream Prelab. In the ice cream Prelab, you're not going to set the Q for water, for the salt water, and the Q for the ice cream mix equal to each other. Okay? You could do that if you knew more about what you're doing, but we're not going to try to do that. Okay? Here's what you are going to do. Well, let's talk about the way that ice cream, freezing ice cream. How many of you have made homemade ice cream before? Okay. Good. Several people have. If you haven't made homemade ice cream, look it up. There are videos on YouTube, okay, making homemade ice cream. In general, a homemade ice cream has this look to it, okay? You have an inner container that you put the ice cream mix in. And the ice cream mix it has a closed top, and there's a paddle inside to kind of keep stirring up the ice cream. And then you, excuse me, you have an outer container that this inner container fits down into, and you put the salt and the ice and a little bit of water in there. Okay? So the ice cream mix goes in here, it's liquid, and the ice and salt and water eventually have to get this cold enough, which means that now most of the time we think about we have to get the ice cream colder. That's not really what's happening. Okay? What's really happening is we're having to get the heat out. All right? To freeze the ice cream, you got to think about it in terms that the way scientists think about it, and scientists think about it in these terms, we're getting the heat out. Okay? And this ice cream freezer here is a lot like our little mini universe here. Got it? Okay? So this is our little mini universe ice cream maker. Now we won't be using one exactly like this, but it works the same way. So we've got to get the heat out in order to get this to freeze and have ice cream. Does everybody understand? All right. So what you need to know is, there's all this stuff in the outer container. Is it capable of taking enough heat out to freeze the ice cream inside? That's the question. So first thing you have to do is figure out, how much heat do I need to remove? That's one problem. Then you look and see, well, how much heat can I put into this? That's the second problem. And compare the two answers. You understand? That's all there is to it. And don't make it harder than it is. Listen, the math is the easy part. It's figuring out when it works and when it don't work. That's the hard part. Okay? So get the math done, which that's going to take you most of the time. And then if you need some help with the thinking it through part, the analysis part, you can come see me. I'll help you with it. Got it? Now, yes? You're going to post your answer online, and there's a link there on the document that I gave you that gets you that links you to and takes you directly to the online document to put your answers in.
Will it tell you if it's wrong?
It won't tell you if it's wrong. I will tell you if you're wrong. I will go in and analyze your answer and find out whether you're right or wrong.
So when do we have this done?
Okay, before we make the ice cream, you have to have it done.
Is it Friday?
Right now, either Thursday or Friday. Okay, so your homework tonight is to do the math. Now listen, don't go getting all upset. Listen to me. Okay? Yeah, you got to do the math on paper, and then put your answers on the document online. Okay? Now look, a couple of tips for you. Please listen. You might even want to write a few things down. A couple of tips for you that's going to help you. All right. Let me find a copy of one of these here. All right. So you're going to have a mass of ice cream mix and the enthalpy of fusion of the ice cream mix. That's the phase change enthalpy, okay? You're going to have an initial temperature of the ice cream mix, and be careful because it's supposed to be a negative number, okay? And I think everybody has negative 10 degrees, right? But look at the negative, the return didn't hit there, so make sure you know the negative belongs in the next line, okay? So on this one right here, the negative's up here, but it applies to this number right here. You got that?
Is that the same thing for degrees and temperature?
Yeah, those are the freezing temperature of the ice cream mix is going to be also 10 degrees C. So here's the point of that. We have already cooled the ice cream mix down to the freezing temperature, but it's liquid. It hasn't gone through that phase change to make it a solid. Okay, that's the point. You with me? All right, now, when you look at the salt water mixture, we're going to eliminate the ice altogether. And we're going to start with a saturated solution of salt water that has an initial temperature of negative 21 degrees C. Okay? That also happens to be the freezing temperature of saturated salt water, but you don't need to know that. Okay? You don't need to know. That's the freezing temperature of salt water. It doesn't matter. Okay? Got it? Doesn't matter. All you need to know is that salt water can't get any warmer than the freezing temperature of the ice cream. All right? If it gets any warmer than the freezing temperature of ice cream, it won't freeze the ice cream. That makes sense?
Yeah.
Because you've got to have an equilibrium temperature at the end. So this ice cream maker is a kind of mini universe, okay? A little calorimeter of sorts. All right? So you've got to have an equilibrium here. So the salt water on the outside here can't get any warmer than the freezing temperature of the ice cream mix, and that's your range. So when you do the math, you're going to assume a final temperature for the salt water of the freezing temperature of the ice cream. That make sense? All right. In the time remaining, let's talk a little theory.
Okay.
In the time remaining, let's talk a little theory. Now we're going to talk about the behavior of water here, and while the values, the numeric values that we're going to be using are different for water than for other things, the theory is the same for just about all substances. Okay, I hope you haven't put away your notes. Hint, hint. Okay. What I want to look at is when you're adding heat energy, in this case to water, what it's doing to the temperature of the water. Okay? So I'm going to put down here on this bottom axis, this is my change in heat energy. Alright? So I have, on this axis, I'm going to be adding heat energy in this direction. Does that make sense? Alright? And on this axis here, I'm going to be looking at the resulting change in temperature as I add heat energy to that water. Okay? And we're just going to have two markings on here, one for 0 degrees C and one for 100 degrees C. Okay, so this is 0 degrees C, and this is 100 degrees C. So what happens at 0 degrees C for water? It freezes and it melts. Okay? What happens at 100 degrees C? It boils. All right? So if I start out with some temperature that's below 0, and I add heat energy to it, what's going to happen?
It's going to melt.
Well, if I'm starting out below 0, it's going to warm up first. It is going to melt, but at first it's going to just heat up. So we're going to heat up until we reach that temperature where we have the, it will start to melt. Okay? But while it's melting, the temperature doesn't change. You keep adding heat to it, but the temperature is not going to change while you're melting. So the heat's just being put in there to get things to melt. Okay? Now once I've melted it, so I've got it at 0 degrees C still, but once I've melted it, then the temperature can go up again. Okay? Until I reach that point where it begins to boil. Okay? And guess what happens when it's boiling? The temperature doesn't go up anymore. So we're going to this boiling point when it's turning into a gas, but the temperature's not going up anymore. Okay? Once I've got it into steam, and I keep adding heat energy to it, then the temperature can go up again. Got it? Now here's the cool thing, I think it's cool anyway because it makes our life a little bit easier. There's only two equations to define all this. Okay? The change in temperature equation is Q equals mass times specific heat times the change in temperature. Okay? And that equation defines the behavior in this range right here, and this range right here, and this range right here. And then we got the Q equals mass times the change in enthalpy. And that defines what's happening here and here. And the only difference here is, of course, the change in temperature is going to be different in each of these ranges, but the specific heat is different for each of these. Okay? So this range here has a specific heat that's different from the range in here, and it's different from this one. And the enthalpy, delta H, is different here and here. Does that make sense? And so if you understand this big picture idea, the rest of the math starts to, it's a little bit easier, because it's not like 5 different equations, it's really only 2. You just have to know what the CP and the delta H are for those ranges. Does that make sense? All right, then now you can pack up, guys. I hope this is in your notes.